Well, hi, and welcome to my shop on March 19th, 2020. So I have an offer for you. Here's my offer. What do you say we spend the next hour ignoring the virus threat that surrounds us all and pay attention to this radio? We'll hide away in this radio for an hour. That's what I plan to do. You're welcome to hide with me for an hour. So, I think the first thing I want to really look at with this radio is the hot chassis situation. I had this radio in another room in my house, outside of my shop, where I didn't have an isolation transformer handy. I just plugged it in the wall. Let's take a look at the plug here. When I went to plug it in, I discovered, in fact, this has a polarized plug on it. One prong is wider than the other, but this is not the original. I'm sure this is not the original cord also. So polarized, this is a 5-tube radio, no transformer, no power supply transformer, series connected heaters, and so I'm quite concerned about voltage on the chassis. So being wise enough, I've had enough experience with this kind of stuff. I brought along my voltmeter down to my other room there. Plugged this in, took the voltmeter, held it on the chassis, held it on my antenna, read 118 volts AC on my meter. Pulled this out, flipped it around. Can't flip it around because it's polarized. So I have a little cheater. I don't have it handy here to show you, but it's just an old splitter you plug in your outlet long before there were 3-prong plugs. It's 2-prong, and you can shove one of these in either way. So I can use it to depolarize a plug. And so I did that. And so I plug it in. I plugged it in the other way and measure 1 volt between the chassis and my antenna. And I proceeded to leave it that way. Well, leave it that way for a short while. I then turned it on because I have enough experience with this. I then turned it on and noticed that the voltage had returned. I then reversed the plug back to the original way with the radio switched on and saw the 1 or 2 volts again. This is the thing about these radios and non-polarized plugs. They can go in either way, and the effect on the radio is I'm not sure I can finish that sentence quite right. Let's just say if you're not careful, there'll be an effect on you from that. So you can have the radio turned off, test it, go, hey, that's great, turn it on, and there's that voltage. Now the voltage is getting there probably through a capacitor. So we're going to take a peek at the schematic again, even though I've examined this once. We're going to examine it again. Then we're going to look in the radio and try to find the parts that are responsible for chassis voltage, if there is such a thing in here. And then we're going to do a little experiment and just see how much power there is behind that voltage. Then we're going to try to get rid of it or return the radio to either its original operating condition or an improved operating condition based on the fact that this is polarized and there's some control now on which way this goes in the outlet. Well, that's my plan. Well, as usual, my plans usually last about a minute into the work, and then I'm off in some other direction. So hopefully that's not going to happen. This is a pretty basic thing. So step 1 was look at the schematic and try to identify how the chassis wiring or chassis is involved in the wiring of this radio and get it kind of get it correct. Here we are. Okay, here we are. Now, going down to the schematic here. Right away, I remember this sitting out here. Let's take a look at this. Not too complicated thing. So here is a capacitor, C24, 0.05, tied between the chassis and the B- and paralleled with a 500,000 ohm resistor. It's a very, very typical way of making these connections. Now I'm interested also in the 2 shells. I think we saw they're connected directly to the chassis. So they drain into the chassis. So failure to drain the chassis properly would result in signals even on the shells of these tubes. And that could be a large part of the problem here. Basically, a chassis that's just singing along with radio frequency signals in it and showing this full voltage effect. So how do you get a full voltage effect? Well, I'm using a high impedance meter to begin with, so you may get a full voltage reading on the meter, but in fact, if you tried to draw any current through it, you're drawing it through this 500,000 ohm resistor, you're not going to get much current. So it may be kind of like a false sign. Although in most cases, my experience with radios with this kind of chassis arrangement is your voltmeter would read 60 volts, 50 volts, 70 volts, something like that, somewhere in the middle or half of 120, half of the supply voltage. That not being the case makes me think this is potentially shorted out or leaky, very, very leaky. But how leaky is it? Could I kill myself with this radio? Could somebody actually kill themselves with this radio? And it's not an easy question to answer, because the amount of current flowing in your body, which is what's going to kill you, depends on lots of factors and how you make contact with whatever it is you're contacting. And there's lots of issues. So would it? Does it have the potential? Maybe that's a better question. If I were to take my bare foot and lay it on my concrete floor here, and then take my hand and lay it flat on the chassis, would I draw enough current through this arrangement to send me to my demise? That's what I want to explore a little bit with this radio. I think the answer might be yes with this one, and that's why I want to explore it. So we want to find this C24.05, and if we can, and maybe this is right on it. Sometimes these things are put right on the capacitor, so you can find them easy. Other times not so easy, and there's no hint in here as to where it is. There's no diagram in here, is there? There's no diagram showing where something like that is. So we'll just have to try to hunt it down. What's the hint? Well, the hint is it's soldered right onto the chassis. Let's go hunting for chassis solder points. We'll find, oops, not there. We'll find this connection, find this capacitor, maybe find this resistor. Okay, let's go do that. Do you see it? I'll now take a beautiful colored pickup stick as my pointer today. So now I've seen some chassis connections in here. So I can see a big solder blob here on a terminal, on a bracket terminal that's holding this big coil and capacitor arrangement. Here's another bracket screwed down but not soldered. I've soldered this because it's carrying important signals. So that's on this coil. So one of these coils is the antenna coil, and the other one will be the oscillator coil. Which is which at the moment, I don't know. So I'm still looking for more solder spots. Especially I'm looking to see if any of these tube sockets are soldered. They're riveted to the chassis. In some radios there'll be solder put over top the rivet, and then these connections, which I don't know if you can really see them on camera or not. There are handy, let's call them chassis terminals, that are available on a lot of these tube sockets. They're not used in this radio. None of the tube sockets are soldered down. What about the number one tube? Okay, so the number one tube. It's this one here, and there is something a little odd. I don't know if you can see that or not. Let me look in the camera here. Something pretty subtle going on. So up and behind this resistor, it's hard to see it. There's a metal strip here that's under the rivet for this socket, and the metal strip. Oh, you know what that is? That's one of the gimmicks. That's one of the gimmicks. Let me get better lighting on here. There, now you can see it. So there's a metal strip coming back from this tube socket, and then it wraps once around this wire. This wire, look at this wire. Look, here's another one. Here's the other gimmick. You got that on camera? Yes, I do have it on camera. There's the other gimmick. So it's just a wire, just wrapping. So I think just from what I read, I'm going to guess this is the one that's supposed to generate some oscillations to mimic a beat frequency oscillator. There's some trick involved in this, and not just a little wrapping a piece of wire. There's more trickiness to it. Not your usual BFO. Usually a BFO is a separate oscillator, and the signal's fed in from that oscillator through some kind of variable control for strength and for frequency. This is kind of a fixed thing, and they're cheating some kind of oscillation into the radio with this one or with this one. Maybe I got them backwards. So was there two? I think there were two gimmicks, and I spotted them both. Way to go. Way to go, Jim. There's probably three gimmicks, and I shouldn't be patting myself on the back yet. Okay, back to what is soldered to the chassis. What is soldered? So this coil bracket is bolted down here, but no soldering. The other bracket's over here. You can see it better in the camera. It's soldered. See, there's a lot of wires hooked up at this end, and not too much hooked up at this end. There's a shielded audio cable running through the radio here, and the shielding is nicely soldered right to the chassis here. Comes up here. Now how about that? Where's that capacitor that's soldered? That must be in here somewhere. The 0.05 capacitor. Would it be near the power cord in some way? Not necessarily. It's going to be attached here. Look, so this one attaches. It does attach to one of those terminals I was talking about. One of the socket terminals that's actually riveted, but they never did solder the rivet here. So I think this is the chassis capacitor. So this would be B minus. How can we prove this is B minus? We can trace all the way. Well, there's a lot of wires hooked up to it, and actually this terminal is shared over with this terminal. It's the same terminal. So lots of things hooked up. That's a sign right there. There's a B minus. Lots of capacitors ending in these connections. 1, 2, 3, 4 of them. That's another sign it's a B minus. Another way is to prove it with a ohmmeter. Let me do that. Use a cook lead here. Don't think it's going to go to 0. Ooh, that's bad. That's no good. We can't use this. Another cheap cord that needs a repair. Let's try, hey, how about real? Real meter. Leads here. So, is this a B minus? This terminal here. And this is definitely B minus here. Now you see a 0. So, no question that's a B minus. Point. Hey, now let's just, I got the ohmmeter out, let's just measure B minus to chassis. So we should see 500,000 ohms. We can go from here. From where? A little too close here, Jim. So I'm just picking the negative terminal of the filter capacitors to the chassis. Not shorted. To the chassis. So there's the resistor, 500,000. A little hard to claim there's something wrong here. The capacitor were shorted, we wouldn't get this reading. If the capacitor was super leaky, I would pull this down a little bit. So we're going to try something else here. I'm using a high impedance meter to make this measurement of the 110 volts on the chassis. Not knowing just, what the, you could look at it this way, if you think of it as a supply, a power supply with an internal resistance, you don't know what the internal resistance is. You could think of it that way. It's probably very high. It's probably 500,000 ohms. So I'm going to get another meter. We're going to repeat the measurements. I'm going to plug this into a regular outlet. We're going to find out what the story is here. And I'm just going to get one of my other meters. To hunt it down. Okay, I'm going to stop and get everything set up for this. Okay, so here's my alternate meter here. This one, it says right on it, 2,000 ohms per volt. So it'll be interesting. That's not terrible. Now, we're going to plug this guy right into a regular outlet. So at that point, it's a danger box on my bench. I want to remain conscious of this fact. Okay, so I'm plugging it in. It's polarized. No choice. How to go. And it goes. No choice. Okay, it's just plugged in, nothing more. I'm going to take my voltmeter here. I'm going to connect one side to the, you can call it power system ground, house neutral, whatever you want to call it. We're going to hook this up to something that's not going to come off in the middle of me doing this. What's a really nice, I need a much better terminal for this. Don't I have something just for that purpose? I think I do. Yeah, here we are. Unfortunately, it's red. So, now, that's right. Okay, so the black lead to my voltmeter is hooked up to the hydro ground. Radio is plugged in but not turned on. I've got rubber sole slippers on. I'm standing on a rubber mat on top of porcelain tile on top of concrete. There's no way I would do it. You know what? I can't even. I'm so sensitive to this stuff. I can't walk around my house in sock feet and touch anything. It doesn't matter what. Like if I'm in sock feet, which I never am. If I were to go and go to grab the refrigerator door, I would hesitate because I'm just so concerned. That's what happens to you. You get a little crazy as you do this for too long. What do we get? Dun, da, da, da. Wait a minute. We can get this on the ohmmeter. We want this on the voltmeter. That's a whole lot of nothing. Now I flipped the plug around, but I can't because it's polarized. Did I do something wrong here? It's not what yeah, I did. Good, let's try it again. Even less. My meter's been a little funky lately. Let's just be sure of it. Nothing. Okay, I'm going to switch it on now. Oh my gosh. I don't have to switch it on. It is on. Son of a gun. Okay, so this is the on state. That's pretty good. I'm going to switch it off. Doesn't look so good. That's the thing about these 5-tube radios is, if you think you've got it safe, just flip the switch to the other position. You'll probably find out you don't. Now, the question is this really enough to electrocute somebody? So electrocution, to kill yourself with electricity, and again, this is not a simple thing. It's a complicated scenario. A few milliamps have to pass through your body, something like that. So now my meters only require microamps, right, to operate, like this one. So we can certainly get microamps out of that. 121. Oh, my cat's calling me already. No, I don't want to stop right now. So we're going to take the lower impedance meter here. We'll see if there's enough power to drive this meter. Literally, that's what we're doing. That's what we're going to find out. I think the answer will be yes, because the meter turns out to be a little better than I remember. This is not my old meter from when I was a kid, but it was just like this. Put this on AC, 150 volts. Clip the ground on here. Okay, my cat's giving up on me. What do you see there? So on this meter, if I can find the right scale to read, so 150 is on this lower scale, so it's reading right up there at 100. This is 130 volts on this meter. So there's more than enough power to operate this meter. So 2,000 ohms per volt on the 150 volt scale is once again beyond the capacity of my brain here. So 150 volt scale times 2,000 ohms per volt equals, so that's a 300,000 ohm 300,000 ohms there. So this is not really proving what I want to prove. What? Your buddy's down there. Shadow's just over there. Go play with Shadow. No, come on. Really? Okay, you know what's happened now? You can continue watching the video when I get back, but I have to stop and go watch the news for a bit with Peanut. Peanut wants to see the news. Is that right, Peanut? Peanut? Is that what you want to do? Yeah, I think you said news. Oh, for crying out loud. I'll be upset when I get back. The 200K. What about another scale? No, it won't show up. 200K. That's interesting. That's similar to the size of resistor that's in there. I thought I had a lower reading. I must be drying out in my older ages or something. 150 megohms. That's way higher than. I haven't watched enough news. If I watch more news, that resistance will come down, I'm sure. So what does all this mean? So when I add all this together, it means there's a voltage sitting on the chassis as high as 120 volts. When you make any connection to it and try to draw any current, the voltage drops almost certainly across that 500,000 ohm resistor. You can only draw a trickle current. The trickle current appears to be as much as 5 milliamps if you had no resistance. You have some resistance, and you can see my test on these. I'm a pretty resistant guy apparently. Stick my 150,000 ohms on here, I just don't think I would draw 5 milliamps. So what do I think in the end? I think this is a dangerous radio. I think this is a dangerous chassis. I can't prove its safety. I can't do something. Hey, where's one of my cats? Come on here and be useful. I can't know for sure. I don't think it is. It's basically in the state, I believe, it was in when it was brand new. You know what? There is that capacitor I have not done anything with. Let's remove that capacitor, the chassis capacitor, and check it. Let's do that. Obviously, I'm on my way to replacing it. This will probably be the whole deal with this video. At this rate, I'm really going into this a little more than I would normally. So it's this guy right here. Nip him off here. Nip him off here. This will be our first sample capacitor too from this radio. See what kind of condition they're in. Is it a 0.05? 0.05, just as specified. And this looks to be in pretty good shape. It really does. Standard Condenser Corporation, Chicago, Illinois. Lots of stuff used to come from Chicago, Illinois. Now China. China. Now, this is a not a quantitative test, but I've done so many capacitors. I've got a notion of its calibration and what good, bad, and ugly is. If you haven't seen one of these devices before, this is an old style machine for doing exactly what I'm doing, checking capacitors. It checks them in two ways. One is you can apply a high voltage onto the capacitor, and a good one leaks no current through it after charging. There's no leakage. Bad ones leak, the leak shows up on the eye. That's the first test. The second test is to actually measure its real capacitance. The second test can only be done if it passes the first test. Okay, so we just ignore what's going on with the eye. Make sure this is set for standard capacitors. We're on the 50 volt setting that says 25. Now the eye should snap closed, pop open just like you see it now. If it's a goodie. Well, there's a lot worse capacitors in this world. I'll move this up to 150 volts. I don't think it'll open. So it's showing what is very, very typical for capacitors coming out of a radio like this. Now, is this enough of a leak for somebody to get a shock through it? It's the same question. I think the testing we did sort of suggests no, it's not. But why don't we just put a ohm meter on this, which I think I can do, easy enough, by just turning this. Let me turn this till it opens. It's right down near the end of the dial here. That's not very good. The R times 100. So this is 1,000. Where's the R? R is on the outside. So this is 50,000 times 100. Whoa. That's a pretty high resistance. 50,000. So it's 50,000 hundred. 500,000 10. 5 million. So it's reading 5, 10, like 10 megohms or something. That makes sense for a capacitor. It's right off scale basically. It's off scale on this thing. What if I open this up? Does it even... Yeah, see, it's just off scale. That's a bogus. Let's try another bogus measurement here. I would think this is bogus. Just try to read the resistance this way. Not sure it's a meaningful test. Although it is basically what that other device was doing. It's just the magic eye makes that other device really, really sensitive. The tiny leakage currents affect that eye. Let's see what happens here. Don't fall over now, meter. $17 megohms. So that compares, you can compare that to the resistor it's in parallel with. This is way, way higher. So part of the reason I'm dwelling on this is because I encountered this 110 volt reading in the midst of trying to use the radio, and I just got very panicky. Not panicky, but I got quite concerned about it. And I just really wanted to really dig into this. No surprises. No surprises. I will put a new capacitor. The type I will put in there is a Y-type capacitor, if I have one. Y type and 0.05. 0.05. 0.1. 0.02. 0.1. 0.01. 0.02. Hey, I haven't got one. Let's sit on my little box. 0.05. There we are. 0.05 Y type. Safety cap. Now, is this going to affect the operation of the radio any? So, you know what? I never tested the capacitance of that meter, that capacitor. Really, no reason to think it's not correct. Okay, so we're going to read the resistance of this. I'm sorry, the capacitance of it. 0.02 on this scale. So I know you probably can't see anything happening, but the eye is dimming ever so slightly right here. So when I do this with leaky capacitors, the eye is supposed to pop open when you hit the right setting, but it won't with a leaky capacitor. And generally they tend to read higher than they actually are. Now this one is coming out based on this probably false reading right here, and the scale is 0.5 scale, so it's 0.1. So it's reading 0.1. It's supposed to be a 0.05, so it's reading double its capacitance. And I think it's just because it's leaky. And, you know, that's why I normally don't read the capacitance on here with these old capacitors, because the test is false. It doesn't mean anything. So back to that question. Can this radio kill somebody? 5 milliamps. How do you get 5 milliamps? How do you get 5 milliamps? How do you get 5 milliamps? Let's do a little calculation here. Is that really realistic? Would they have designed this radio so it'll give you a 5 milliamp shock? I don't think so. So we got, we want to know the current. I equals E over R. E is 120 volts. And R is 500,000 ohms. So we divide that by 500,000. Okay. We get, so we get 0.2 milliamps. Whoa! And get the lights on here. That looks like 0.2 milliamps. So I'm going to guess 0.2 milliamps is what we would refer to as a tickle shock or a brush shock. Brush shock happens because people brush their hands up against things, and just like that static discharge you could hear, you can feel it a little more if you do this than if you just do that. And I'm doing that. I'm not getting any shocks. Hear it? I hear it in my headphones. So, you know, I think when I do something like that, something has a bit of a charge in it. Could be the chassis, could be me, could be static charge. And you touch, the charge is shared immediately, and that flow causes the tick you hear. Take your hand away a moment later, you can do it again. Pretty subtle stuff. Let me charge myself up. Oh yeah, hey, you know what? I felt that. Yes, that's what I'm doing. Doing a little jig here. That's too much of a chicken. Lots of funny things, eh? What a crazy time. I put this capacitor in. Hey, this chassis doesn't have its capacitor anymore. Hey. Let's fix all that up. Okay, so I have the capacitor installed here, soldered in place, no problem at all. We should take a look at the schematic because I think there's another capacitor or two that are tied to the chassis in here. And right away I can spot this one, right to the chassis. There's these connections. So the chassis also, but they're a little different. But we got to find this capacitor. Here's a, well, this is probably a mica capacitor here. Probably don't have to worry about that. Lots of connections to the chassis. Now, connections back to the B minus. There's probably only the one. Where'd it go? And they show it like this. Is that really true? So if we get on the B minus line, and we look for chassis symbols, not likely to find any. Oh, okay. So this one is talking. This one is just covering the shield on the wires here around the voltmeter. That's another connection from the tube metal shield can to the chassis. Oh, look at this one. Another one here. Oh, okay. So the asterisk means. Oh, see, asterisk means this is in that couplet. This one's there too, in the couplet. This one's in the couplet. 1, 2, 3, 4. Oh, wait a minute, how many are in there? Is that the couplet? That is the couplet. Part of couplet, C11. Couplet, C11. 1, 2, 3, 4 capacitors. 1. Nothing to do with the chassis though. 1, 2, 3. Mine, I think I saw 6 of them here. 6, and the last one's way over here. 4. Why? Why do these have to be in a couplet? The couplet is pretty boring. It's just capacitors. Capacitors that happen to share some common leads here. Shield. Not used in circuit. So I think what they're saying is there's a wire. I don't know what they're saying. It's dotted. This must be an internal thing, and like a metal internal shield inside this structure, shielding this one from the rest. I think I'm probably on my way to changing all these. I might be anyway. So the one that's concerning me though is just making sure none of the other ones are involved with the chassis. Just this one. 0.005. We could just do one of them. 0.005. This one. From 1 to 2. If we can figure out the numbering. So they're showing the words on the front and then they're showing the number order. So I think that's what they're showing here. If I can find these words, I can figure out pin 1 from pin 6. And then I could go after this 0.05 and eliminate it. Is this really, is it the same thing as a safety concern? It's not tied back to B minus. Maybe it's, oh, B plus. Well, we certainly don't want a failure in this capacitor. If this capacitor were to short right out, goodness knows exactly what would happen, but you'd have B plus for some period of time sitting right on the chassis. The chassis is connected to B minus through this resistor. Now, I don't think that would cause the resistor to burn up, would it? Is that the idea of this? This is a fuse? And if you do attempt to liven the chassis up, this guy will take care of the situation? That's an interesting question. Is that what that's for? Calculation time. Calculation time. Calculation time. Can't do it without my calculator. Here we are. So the question is that resistor designed to burn out if the chassis should be made live? So there's a couple ways of going. How much current would it take to burn out that resistor? How much voltage would it take to burn out that resistor? So it looks like a quarter watt. I don't know where it is. We're going to assume it's a quarter watt. Well, we'll see how much wattage. 500,000. They put B plus across it, 150 volts. Let's use that. 500,000, 150 volts. What current do you get? So I equals E over R again. So 150 volts. And divided by 500,000. So the current, again, is less than a milliamp. So if we square the current, let's use a milliamp now. We'll use a milliamp. We'll jump it up. Use a milliamp. 0.001 squared. There's no squared button. Times 0.001 times 500,000. Half a watt. Half a watt. Just right in the gray zone. What happens if you dump half a watt through a quarter watt resistor? Well, I don't know. That didn't answer that question, did it? It's sort of maybe. That's kind of where it ended up there. Yeah. Nothing you would rely on to operate as a fuse. A lot of radios have 1,000 ohm resistors stuck in the B plus leads going to the tubes, and that gives you offers you a couple of advantages in troubleshooting. One is the voltage drop tells you the current flow through it, so that's probably the primary reason they're there. But also they can burn out if you have a heavy fault. And then often they're positioned where they're really easy to find too. And I'm thinking about European radios, these 1,000 ohm resistors in them. Okay, so the situation now is I have to make a decision around the couplet. The couplet. So let's take a look at it. There it is. Okay, I can see the words. I don't see any terminal numbers, but it would mean terminal 1 is here on this end. 1, 2, 3, 4, 5. Is that right? Five terminals? That doesn't make sense, does it? 5 terminals. I'm just going to glance at the manual here myself. 5 terminals. Would it be 5? It would be 1, 2, 3, 4, 5, 6 terminals. 6 terminals on here. Let's try that again. So 1, 2, 3. There's a space here for 4, but there's no 4. 1, 2, 3, 4, 5. Well, how's that going to work for me? Number 6 is there? No, they all come out the same end. Number 5, where is it? Is it hidden under there? Okay, well, that's a mystery. So there's a number on here, and there's 2 of them in there, 2 of them in the manual. The number here is 47. Looks like 47A581. 47A581, and the number 47A581. There it is. There's a 5-terminal version of this. This only has 3 capacitors in it. Huh? I found 4 in the radio. Oh, okay, so the schematic is based on the idea that there's 4 of them here. I'm going to put this on the screen. So here's the number I could read, 47A581 right there. 5 terminals, like what I counted. This is what's in there, 3 capacitors. Well, the schematic shows 4. So the schematic is based on this. What's it say? Couplet used on Mark 1A sets. So I do not have a Mark 1A set. Used on Mark 1B sets. I have a 1B set. When replacing the couplet, use 74A5A1. Use this one. Illustrated at the right, the new couplet eliminates one capacitor section that is not needed. Terminals 3 and 4 were grounded. Terminals 3 and 4 were grounded. Oh yeah, not used in circuit. Okay, so it's only 3 here, and this one's missing. So still we have the same thing. It's still between the first and second pin is a 0.005 capacitor that is actually tied to the chassis. Now, how do they do that? Did it tie this to the chassis? Can I see one of these terminals is on the chassis? So one of these terminals going to the chassis. We'll just trace them all. So here's the first one. Hey, where's my pickup stick? Yeah, today's pickup stick day. So if we want to follow an order, this would be terminal 1 goes to a 2 pin. Terminal 2 goes to a 2 pin with a resistor. Terminal 3 goes rather sloppily down to this terminal. Lots of wires on that one. And just go over this way. What do I see? I see this big filter resistor hooked up to that terminal, hooked up to a wire, hooked up to this terminal. Okay, and then we come out here. This is the one I think we're interested in. This goes to this wire on this terminal, and the wire goes, oh my god, where's it go? You know what? There's a big honking lump of solder under here. Just right up in here. Wow, we can barely see it. Is that what's going there? What's going there? So it looks like a pile of wires soldered right here to the chassis. Why wouldn't they? Well, they didn't. I was going to say, why didn't they use this terminal, solder that down, and then hook wires up here? Why get them all down yonder there? Oh, it's almost impossible to be sure. Oh, I know how to be sure. I know how to be sure. Surer. Anyway, more sure, more sure. Yeah, sure. People need certainty right now. I'm referring to the... Oh, we're not supposed to refer to that. We're ignoring all that while I'm in the shop. Pretending the rest of the world doesn't exist. Okay, so the objective here is to put this on stable ground. Ground is right. So, is this going to the chassis? Oh, I'd say no. How about that? Somewhere that was apparently I can't form words anymore. Why do I think one of them's going to the chassis? I saw that on the schematic. He says, answering his own question. And have I printed the schematic for this radio? No, I have not. Let's look at it again on the computer screen here. Dot there. They've done the same thing here. Maybe hidden terminals, exposed terminals, I guess is maybe what they're trying to show here. So 1, 2, and 3 should be connected. No, it's a stupid statement. They're all connected. All these are connected. So I think one of them goes to the chassis over here. C26. Are there numbers on here? Yeah. Well, it's not C26. Wait a minute. So it's C11A, C11B, and C11C is what they're doing here. And same thing here. C11A, C11B, C11. So it's C11. Well, that's C26. Why did I... Wait a minute. Oh, what a dummy. This is the one that's contained in the thing. And it's just to the B minus. Okay, somehow I got this little asterisk over here in my head. Okay, so this capacitor is still out there to be found. Or is that the one I did? So the one I did is hooked up to a terminal on which there is a pretty fancy looking coil. Oh my gosh, what could we have? Wow, who knows? I thought it might be that thing. Okay, so I don't really know for sure what capacitor I did, although was it a point? It wasn't a point. It wasn't a 0.005, it was a 0.05. It was this guy, for sure. No doubt. Okay, so this guy's still out there. I gotta find a capacitor that's soldered to the chassis. 0.05. Okay, let's go hunting. 0.05. Hopefully right onto the chassis. So what is soldered down in there? And can I spot a 0.05? 0.005. Can I just spot a 0.005? This guy's fairly small. I'm trying to read the sizes on all the capacitors, but not really in the right spot. Okay, so to the chassis. So what I'll do, I'll use the ohm meter to identify it. I'm going to clip this on so I don't have to hold it. And just check all the capacitors and see which one gives me a 0. Anybody show me a 0? I can make this a little less here. Check it. Oh, for God's sakes. Really? This is going to be the problem? Okay, put that in a pile of stuff to fix later. The right one here. Okay, we're in business now. Let's check this guy. I just put him in. Good. First I didn't see the 0. What's happened? These I can see, just can't be connected to the chassis. I can tell what they're doing. Uh-oh. Nobody's showing up. Is it possible one of these is big enough to be that capacitor? Some pretty big ones in here. Oh. should be up on top. Could it be up here? I don't think there's anything up here. Once in a while there's a capacitor stuck around the tuning capacitor. But there's nothing in this radio. There's nothing up above. So where is that capacitor? If it really exists, or now you know what? I'm looking right at it. I'm looking right at it. Okay, I see it. I see it. I do. It's this. It's this one here. I can see 0.005 written on it. And I can see, yeah, one side's going right to the chassis. There it goes. You see the meter. You don't see the meter anymore. The meter is showing 0. It was showing 0. So that's clear. I can see it. It tests that way. The other side, it's a ceramic capacitor. I'm not going to worry about it. It's laid flat. It's obviously a critical. Its position is critical. So now that capacitor, what is that capacitor actually draining to the chassis? Let's go back and look at that schematic here and see if we can figure out how does this work. So I think I've mentioned in the last couple of videos, I don't fully understand why the front end of a lot of these radios are down to the chassis, but later on it's all B minus. So why like that's a B minus connection, and that's a chassis connection. And I don't have an answer to that question. Don't even know if it's even all that important. Lots of chassis connections. So the 0.05 is draining out this. This is the B plus. Well, I guess it's draining the B plus. I guess, you know, maybe the way to look at this is there are some signals, some electricity trying to get back to the B minus. And because of all these chassis connections, there's other signals or electricity trying to get back to the chassis. So maybe this is to allow signals that have worked their way onto this B plus line to get to where they want to go. So with this capacitor they go to the chassis, and with this one they go to the B minus, because they really are hooked the same here. So then in effect you have B minus to the chassis with a capacitor, and B plus to the chassis with a capacitor. Maybe I've seen this over and over, I don't realize it. So that one is a ceramic capacitor. I'm going to trust it and not worry about it. If it were seriously defective, really defective, we'd have no B plus in this radio. Okay, just beat this issue to death here. I really have. The issue of the chassis and its connections. So the manual contains information about voltages on the tube socket voltages, tube pin voltages. I think I'm going to avail myself of that next. I'm going to run the radio, measure those voltages, compare it with what they're supposed to be, and then I'm going to set about trying to correct things by changing these old capacitors. Even you know what? Even changing this may have affected some of those weird things. So maybe the next step is to play this radio again and see if this alone has made differences in its operation. Yeah, why don't we try that? The last radio I changed too many capacitors at once and got myself into a lot of trouble. I don't want to do that again. So, okay, we're going to play this radio. Shouldn't pick anything down there. Go up the other way, Chan. This time of day up this way.
today were being...
Bunch more in here. I gotta really think. This is the band that should be over here, just coming in over here. I don't think these are images or... And I'll have to come in here in the evening to be more sure, but it seems to have cleaned it up. There's only one signal to hear though. Okay, so what if we give it a... I'm not sure how this makes sense. We'll hit it with a 7 megahertz signal here. Okay, so 6.6 showing up at 7. Now I'm going to tune the signal generator up through the band, down through the band, and see if we hear it again in here, anywhere, with a strong signal. Strong signal, but the signal generator is not connected directly to the radio. That's the 6.6. Okay, let's check this out. So the real one is 6.6, wasn't it? Let me turn this down. 6.63. 6.63. 75. So 455 doubled is, come on, Jim, 910. So if you pick the same thing up 910 kilohertz apart, one of them is an image. Almost certainly. Let's try this again. We start at 6. 663. And so 663 plus 910. 75 something. 75 something. There it is. Oh, son of a gun. So that's the image coming through. Now we're on a shortwave band. The IF is frequency is only 455. So the image is not far away from the tuning point. So the response of the radio can't null out the image. Especially this radio. No loop antenna, no RF tube, nothing going on except a wire into the back of it. So I think it's probably characteristic of this radio. It just doesn't have what it needs to control this image problem. And I don't think it's a matter of capacitors or anything like that. Now, as for all that other crazy nonsense, hey, let's take a look at that. Let's see what's happened. I gotta hook up the SDR. Okay, I'm gonna get the SDR going here. We're gonna repeat what we did and see if that one capacitor has cleaned this thing up a lot. Maybe entirely. Okay, so the SDR is now on screen, obviously. That's mostly the AM band and all the usual noise that's in my shop. Now, I'm going to switch this to the broadcast band also. You see the local oscillator showed up, that yellow line, and if I tune the radio you'll see it move. Now, see all that other stuff going on? Kind of jumping up and down, isn't it? Now, I think that's probably ABC action on the SDR. I don't see a whole bunch of stupid things on there. But I think this was mostly happening higher in higher frequencies. So we're going to jump up to, oh, I don't know, I say 5. And without changing the band of this radio, just tuning it. Anything funny going on? There's something funny coming in from the right. Okay, now I'm going to switch to the 1.7 to 5 band. Nothing happened. Next band. Oh, something popped up there around 6 megahertz. I'm tuned The dial's pointing to 8.5. Okay, turning a bit. Whoosh, that thing just flew like a rocket. So that's some kind of product traveling at high speed there. Is that really true? So I'm just ranging back and forth about 200 kilohertz, and that thing is shooting back and forth much more than that. Okay, so if I want to get the local oscillator on the screen, I'm going to go down, down, down until some big thing appears. Is that the big thing? Right around 6200. Yeah, that could be it, because we're tuned to just above. Not nearly as... Oh, what's that coming in from the right? So there's still a few... Oh, here he comes. This is the real McCoy now. This guy. So if we bring him down to here... Wait a minute. That's the local oscillator. It's running at 6.2, and I got the radio tuned to 5. It should be... That oscillator should be 5... You know, if I had the radio tuned to 5, the oscillator should be 460 above. 5460, and at 5460, wow, it's hard to read that screen there. What's going on? Oh, maybe it is in the right spot. Yeah, I think it is. So all those crazy signals and craziness that I saw has all been arrested. Another thing's going the wrong way. Whoa! Look how it crashed. Boom. It's not nearly what it was. This is not nearly what it was, I'm pretty sure. And that's two tests on that. There's a little... Ooh, what's that doing up? It's going the wrong direction. I'm tuning up, it's going down. Well, there still is some pretty sneaky stuff in here. The radio thinks it's tuning 28 megahertz right now. And I'm looking at signals at 6 megahertz coming out of it. Is that a real thing? That thing there? So I'm going to turn the sound on to the SDR and we will hear it. When I cross the red line. That's a hummy local oscillator. So that's something I've never done before, is actually listen to the local oscillator using the SDR, even though I've had, you know, probably 20 opportunities to do that. I've never done it till now. It's kind of an interesting test in itself. A little hummy, eh? So, okay, bottom line of this. Bottom line is, changing that one capacitor appears to have had a major effect on signals radiating out of the radio, and what would appear to me to be signals multiplying themselves through the mixer, sort of running through again and again, kind of mixing themselves with themselves. Kind of an incestuous radio in a sense. So I think that's over. I think that one capacitor had a big impact on this thing. Now what is all that curious stuff on there anyway? These weird SDR dancing around signals. Don't know. I don't know. Let's turn off the radio. That's the last step actually. I'll switch it off and see if anything disappears. The local oscillator went away. Nothing else though. That's actually a really good test. Yeah, I think that one capacitor had a huge effect on the radio. And that's it for today. So that's it. You have to go back to facing the virus situation. The holiday is over here in my shop. So thanks a lot for watching, and tomorrow we'll start on some more of those capacitors.